That's good.
Well, it's not going to just send those in different schedules.
Okay. I'm not sure what you said. Oh, cool. You said something about sending.
Send the rest of them and take a picture of the one that he does.
Does anybody want the picture of 27?
While they're talking, can you go type this 21 to 30 and 35 to 42?
Hey Joyce,
What?
sorry about that gov test.
Type 21 to 30.
And now we're doing calculus, but you had AP French, so sorry.
Executive order
And then
apparently
comma.
not constitutional.
Yeah. No,
35
not that they're
to
not
42.
constitutional. They're not written in the
Oh,
Constitution.
35.
Not written in the Constitution.
They are informal powers. So if you put that on the thing, you're chilling.
Hi Joyce, don't worry, I'm just getting algebra answers up. Okay, so people had questions on homework, but you came into math lab and you had questions too. They are sending pictures out, but we still are kind of stuck on number 33 from section 10.1. So we're gonna go check it out real fast. We gotta go to homework exercises though. As I'm getting their question, how did homework get hard?
Some of the
We don't know how to count.
stuff they had us do is kind of ridiculous.
The integration part was just.
Okay, so explain it to me now. When they said to go back to a previous exercise and then find the power series for the integral, what were you literally doing?
Integrating the power
Using
series.
the answer.
Integrating the power series, which the power series is literally like little baby polynomials, right? In essence, so when you are integrating the power series, you're integrating polynomials. Now, how do you express that as a function?
With the 1 over 1 minus r?
If you can match it to a geometric series, yeah, you can use the a sub 1 over 1 minus r formula. If you can't match it, maybe you actually need to integrate to show the equality. Number 33 just says, do the integral thingamabob for number 23. So let's go back to number 23. George had that one up on the board, so we're going to kind of steal his work on that one. Here is the original series, though, so we can look at it. I think one of the things that makes this homework hard is number 1, not knowing what they're expecting of you, and then number 2, not having enough mastery to know how to jump there. My girls that came and asked me questions this morning, well, Joyce isn't here. Joyce, you're included. What was the advice I gave you for 21 to 24, even though they didn't look like geometric series? Just start plugging in and see if you can recognize the first term and then the common ratio. Amanda Debasarian, how did you think about 21 to 24? It was different, but it was still appropriate.
I was following the theorem that they gave. I was like C for like X and an N, and then like I just followed that. No, I explained it also, but
But using this one, right? This here?
yeah, for like 27 and 29.
Oh, okay. So she was expanding them using the theorem at hand, and both ways are appropriate. Both ways are appropriate. I think the geometric series way is a little bit more intuitive, which is why I like it, but both ways are appropriate. So let's go look at number 23. Okay, so for number 23, we have the series here. Let me go ahead and get to the notes, which is, for some reason, not showing up, and I'm not exactly sure why, so hold on.
George on 23? Why isn't R negative?
Maybe they're wrong.
It's 1 minus r, so therefore the subtraction shows that the r is positive. Oh, or is it not?
Because it's one thing,
Negative
one
one
half
half.
to it to be.
Oh, it's supposed
Yeah,
to
I
be.
missed the
So it'd just be a 1 plus instead. It'd just be a 1 plus. Okay, so using George's work for number 23, you were able to write this series as, what was the function for number 23 real quick? Sorry. Or the series, I should say.
Negative 1 half to the n times x minus 3 to the n.
Where is this one centered at, guys? Just looking at it.
3.
Good. N equals, is it 0 to infinity for this one?
Yes.
Okay. When we plug in 0, anything to the 0 is 1, true?
1. Yay.
The next term was, according to, I'm just going to steal it, negative 1 half times x minus 3. Then we have a positive 1 half. Wait, positive 1 half.
Yeah,
Yeah.
square.
You mean 1/4?
Yeah.
Wouldn't the second one be to the? Oh wait, no.
Told you guys I don't know how to count. Sorry,
We got it.
but it's still the same, right? Because the times one half times half.
Is this a geometric series? Yes or no?
Yes.
Yeah. What's my common ratio?
Negative 1/2 x minus 3 or times x minus 3.
From that, we can use or find the interval of convergence, which Georgie already did. We'll get there in a second. What's my function then?
1/1 minus negative parentheses negative x over 2 plus 3.
Because our initial term all over, and then we have our plus, and then we have our 1/2 and x minus 3. Which we could, of course, simplify if we wanted to, right?
But there's no need to.
And maybe we should for number 33, but maybe it wasn't necessary for number 23. Interval of convergence, we go ahead and take our ratio and we set it in between x minus 3, in between 1 and negative 1. We can multiply both sides by negative 2. Don't we end up with x minus 3 is going to be in between 2 and negative 2?
Yeah.
And so we end up x is between, what'd you get? 1. Good. And that came from, I believe, expanding. Okay, so let's use this for number 33. Number 33 says, hey, it's time to take the integral. Integral of what? Integral of this. Really? Yeah. So number 33, if we want to take the integral of who? That. Oh, thanks. The integral of my function, can we get rid of the nastiness that it looks like right now? Can we multiply top and bottom by 2? Is that okay? So multiplying top and bottom by 2, we're going to have 2 over, technically, to rewrite him,
It's gonna end up
2
being
over
x
2
minus
plus, yeah, I was just going to go ahead and show the in-between step. There we go. And that's going to be x minus 1, right? Okay. Now how do we go ahead and talk about his power series? We just integrate term by term. Really? So what's the integral of 1?
X.
X. What's the integral of negative 1/2 x minus 3? Can't I think of x minus 3 as a u, and so now it's going to be squared instead of singular? Does that make sense? And I need to divide by 2, but there's already a 2, so it's going to be negative 1. Does that make sense? I can go ahead and have my plus. I'm going to add a power, yeah? So x minus 3 to the power of 3. Divide by 3, that's going to be 1/12. Minus, let's do one more just for the heck of it. X minus 3 to the power of 4 divided by 4, that's negative 1 over 32. Now question, can we write this as a geometric series? So better question, is it a geometric series? Because it's to the 4th divided by 4. Oh no, yeah, 8 times 4 is 32. There you go. Is it a geometric series? No. No, it's not a geometric series. Right? Why isn't it a geometric series? Hey guys, look at the integral real quick. We should know who this is. Who is that? Right? Technically plus c, but when they have us doing that snazzy thing where it says a to x, is that what it is? Long story short, that allows us to ignore the plus c. Long story short, that allows us to ignore the plus c, thinking about an initial condition, etc. Now, does that mean that these are always equal all the time? No. What are we going to use for the interval of convergence? The same as the last one until we learn further, which this is at least its interval of convergence. It might be broader, it might be bigger, or it might be the exact same. So for right now, we'll just stop there, okay? All right, cool kids. I think besides that, Joyce and the rest of you, we have answers on the board.
Oh, you did it right.
But here's the thing. It says use a series centered at A to represent the power series for the integral A to x f t. So the power series.
It is centered at A.
Right. No, yeah, but
You did it right. You did it right.
Okay, so it represents the power series represents 2L and absolute value of x minus 1. Right?
power series represents that for a certain interval of convergence.
Okay.
Yes. Does that make sense?
Mm-hmm.
Okay, good.
Now I get it.
All right. Okay, let's go ahead and go back to the original example then that we were looking at. Yeah, is that okay? Oh, that wasn't it. Here he is. Hey, it's an ln. So how do we find a power series that represents ln? You say, oh, wait a minute, hold on. His derivative is a geometric. His power series is, or his derivative is a geometric. Series.
So can we do 1 over 1 minus x and then integrate that?
Do we have that one memorized yet? What's 1 over 1 minus x?
1.
Plus
Start at 1 and then times x and then times x again and then times x again. So if I want ln of 1 minus x, and that's equal to the integral of 1 over 1 minus x, the absolute value isn't there, which makes it a little bit tricky. That just means he has a limited domain. George, go ahead.
What do you plug mu2 to get 1 x minus squared?
Oh, we're starting with the first term, and then we're multiplying by the common ratio, times x times x times x. It is going to be an endeavor card where we could just memorize it, but I think it comes much quicker and easier if we see it as a geometric series. Does that make sense? Okay. This technically has a restricted domain of x has to be greater than 1, right? Anyway, to integrate 1 over 1 minus x, can't we integrate the power series? That 1 over 1 minus x is represented by? So what's the integral of 1? What's the integral of x? What's the integral of x squared? Right?
Absolute value of 1 minus x.
I just said since they stated that they want us to find ln of parentheses 1 minus x, then we're going to just have a restricted domain of x is greater than 1 for the integral. Right? Wait, greater than 1 doesn't make sense. Less than 1. Did anybody catch that mistake? Oops. Does that make more sense? Because 0 works, -1, -2, -3. There we go, that's better. Question, what's the interval of convergence for the original?
1 to 1.
So we're going to use as the interval of convergence for this one until we learn more.
Will we learn how to do
Yeah.
that?
According to our book, and why I'm telling you guys, or why we're doing it this way, is because there is a theorem, if I can get there. It's the one that has to do with integration. Not, yes, this one. The one that Amanda Devassarian was talking about earlier. If an original power series converges for a certain radius or interval of convergence, I should say interval of convergence, then the series obtained by integrating the power series term by term converges for, look, do you see it? The exact same interval. Does that make sense? If the series f, the original series, converges for all x, then so does the series for the integral. If you guys read down a little bit lower, it does ask the question, okay, so it does converge for that interval, does it converge for anything else? That's a question that's kind of leading that they haven't answered yet. Let's get out of this for now, because I think we're okay. Let's get out of that as well for now. There we go. Back to algebra 1. Oh, where'd you guys go? There you are. So interval of convergence, we're going to use the exact same. X is, I haven't really been using inequalities. I don't know why I started just right now. X is within -1 to 1. Is that okay? Making a little more sense? So what have we learned how to do? Which power series to find? Power series that are geometric in nature, power series that come from or are a geometric series, we've learned how to write as a function. And we've also learned how to write series that can, or I should say power series for functions that can be written as a product or a composition of a geometric series. Then we also learned how to work with ln's because those are integrals of geometric series. And then we've worked with other rational functions to other powers, like 1 over something squared or 1 over something cubed, because those are derivatives. Okay. With all of that, we're just going to introduce section 10.2 today. We're not going to get super, super far. But polynomial functions can be used to approximate other things, like sine of x, e to the x, and we've already kind of started seeing ln of x. So rational functions, those go back to geometric series ultimately, right? Because 1 over 1 minus x can be a sub 1 over 1 minus r. But now we're going to talk about further functions, broader functions, and there are ways to make power series that are a lot easier than our methods with geometric series. But we have to define something new called a Taylor polynomial. A Taylor polynomial. So if you guys want, you can go ahead and title, this is going to be section, ooh, not 9.7. What? I didn't change it? Yeah, it's 10.2. Because you guys like getting things in your notes first. Going McLaren? Let's not get a McLaren today.
No McLaren?
No McLaren. You gotta put a bit of an Irish accent on it.
Reminds you of that scene from Indiana Jones 3, Bruce Brand reads some Scottish.
I'm Irish.
Oh, you can break out the
Did you
accent.
say sorry?
Party pooper.
I can't do accents.
It's okay, they're fine.
Josh Williamson.
The very first
Does
year,
the best Scottish accent.
we had Jacob Giganti. I think he's technically somewhat Irish, Scottish something, so he was totally having fun breaking it out.
I'll learn.
Just for McLarens. I don't know if that's Scottish or Irish though.
I don't even
I
know
feel
what
like I
to
might be
say.
like seriously offending one or the other.
Well,
should go ask Madame.
Go home.
Well, if you know the soccer coach for the girls, he's Scottish. Irish sounds more like
Irish.
I think so.
it sounds more proper.
Which one's Madame? She's really mad if you do the wrong one. I just don't remember which one she is.
Then do the wrong one on purpose. Joyce, do the wrong one on purpose.
Please, Grace.
Right now.
Oh yeah, Joyce should know. Joyce, you're gonna let us know.
Please don't be
I
mad.
feel like she's I don't know, I'm getting in trouble. I don't know what she is. She's trying to really relax something. Hey, do you guys see your power series?
Nope.
Wait, why is it not called power series, is it? Oh,
It's not.
power polynomial.
Oh, interesting. I understand.
Interesting.
So a Taylor polynomial is a type of power polynomial.
Oh, hold on. The endeavors from the last section, are they on the notes? Like, do you label them endeavors?
Oh, remember we haven't made an endeavor because it's going to be expanded.
Oh.
So the geometric series is eventually going to be a part of an endeavor, but we're going to put the special power series.
Well, this looks
Together on a card.
There's factorials coming
This
out
one
of
is going to be a
nowhere.
card though, the nth degree Taylor polynomial.
There's factorials coming out of nowhere, Miss D.
What? Why are they coming out of nowhere?
Because they have no factual basis for being that. I made Jackie laugh.
Goes.
This makes no sense.
Okay, geometric series, no big deal yet. We learned how to deal with that in section 10.1. Section 10.2 says, okay, how do we kind of do the same idea but with more complicated functions? Like,
What we were doing were pretty complicated, right?
I agree with Amanda here.
non-rational functions. How about that? Does that sound better? Non-rational functions. Now, we're not going to get through all of this today, obviously, but the idea is, for Taylor polynomials and approximations, I'm going to have you go back to your grapher. I'm going to have you find the equation of the tangent line, Euler's method. The equation of the tangent line, don't worry, it's just y equals mx plus b or y minus y equals m times x minus x1.
Yeah, that's right.
And question, for the approximation of the tangent line, if we graph it, question, is that tangent line kind of getting close to sine
Yeah.
for a certain interval? The question, what if we were to do maybe further polynomials?
Oh, snap. That's pretty cool.
It's even cooler than the other ones.
Oh, wow.
So can other
Functions are
functions
cool.
beyond rational functions and then like their derivatives and integrals be approximated using series? And the answer is yes. And the answer is how? And the answer is Taylor polynomials. And the nice thing is, look guys, it's a formula where you don't have to make it up every time.
Who came up with that formula though?
Go team.
That's the real question.
Like, seriously, what is that?
We need to research who Taylor and McLaren are. Anyway, cool kids, with that, I believe we are done, or we're going to be done in 25 seconds. Let's go ahead and pause there, and tomorrow we're going to jump in.